we're going to continue to compare two samples, but now we'll be talking about two means from independent samples. So in this section, we're going to be using sample data from two independent samples, and we'll hypothesis test and construct confidence intervals to estimate the difference between the two population means. Here, we're going to assume that the sigmas are unknown, and even at the very end, we'll talk about what happens when the sigma is known, and we'll just go back and assume that we don't know it. So in general, it's assuming that the population standard deviation sigma for both samples is unknown for both populations. We'll cover the difference between independent and dependent is something we'll be covering in the next section. So two samples are independent if the sample values from one population are not related or naturally paired with the other, and they're dependent if they are somehow matched or they're based on each other. And so for this one, we're just looking at two kind of different sample situations. If the two samples have different sample sizes, no missing data, they must be independent. If they have the same sample size, they may or may not be independent. So here we're going to be doing a hypothesis test and confidence interval. And in this case, the equivalent methods here are all equivalent. P-value, critical value method, and confidence interval, they're all going to give us the same conclusions. So here is the notation we'll be using here, and because we're dealing with two different populations, we're going to have sub 1 and sub 2. We need sigmas to be unknown, the samples to be independent, simple, random, and that they are either both larger than 30, or normally distributed. So we'll be using the calculator to get the test statistic and the p-value when the null hypothesis has the mean equal to each other. So we'll be using two samples, t-test, because we don't know our sigma, and we'll either use data or the stats depending on the information we're given. What's important here to note is the pooled data, we're going to click no for pooled. All right. And again, wording, we just continue to keep that as a reminder. So listed below are the student course evaluation scores for courses taught by female professors and male professors. Use a 0.05 significance level to test the claim that the two samples are from populations, with the same mean. Does there appear to be a difference in evaluation scores of courses taught by female professors and male professors? So the claim here is that they have the same mean, or that the difference between the means is 0, right? So we can call the females are going to be our population 1 and the males will be 2. So what we're basically saying is that the means are the same, or that the difference is 0. There is no difference. So when we look at the null hypothesis, that is our claim, right? That the means are the same mean. So that's our claim. And then it would be not equal to would be our alternative hypothesis. So let's go into our calculator. And in terms of the requirements here, we don't know the population sigmas. These are independent because they're not paired in any way. It's simple, random. It's small, but these are normally distributed. So we'll go in here and we'll go to stats and to tests. And we're doing the two samples t-test because we don't know our sigmas. Now we do have the stats here. So females are our 1, so our x bar 1, say 3.867, the standard deviation 0.563, and the n is 12. X bar for the second population here, or the second sample, and 0.395, and n2 is 15. Keep scrolling down, and our alternative is not equal to. Pooled, no, calculate. So here we get our test statistic is negative 0.657, but we are going to use the p-value method. So we get 0.519. So our p-value is 0.519. So how does our p-value compare to our significance level? It is greater than, not less than. So we would fail to reject the null. So our original claim had equality, and we failed to reject, so there's not sufficient evidence to warrant rejection of that claim. So it doesn't mean we accept it, but it's close to accepting it, right? There's not sufficient evidence to reject the claim that the evaluation scores are different between female professors and male professors. So they have the same mean course evaluation score. There's not enough evidence to reject that claim. So now we'll do a critical value method example. So for the critical value here, this is the same method that we've done before. The only difference is that for the degrees of freedom, we're going to use the smaller of the n minus 1, so depending on the different samples. And everything else is the same that we've done before. So assume that the two samples are independent, simple, random, and normally distributed. And so they're doing trials to investigate the colors on creativity. So subjects with a red background were asked to think of creative uses, and subjects with a blue background were asked the same thing. So here are the responses, and higher scores correspond to more creativity. And the researchers make the claim that blue enhances performance on a creative task. So the claim is that blue enhances or makes it greater than red. So we're going to make blue 1 and red 2. So our null hypothesis and our alternative, so the average for the blue would be higher than the red, and then this would be equal to, and this is our claim here. So our blue is 1 and our red is 2. So we'll go straight into the calculator. So we're going to go into stat tests to sample t-test. And our x1 here is x bar 1, 3.97. Sample deviation, 0.63. N is 36. X bar 2, 3.39. 0.97. 35. And then our alternative here is greater than. Pooled is no, calculate. So our test statistic here is 2.98. So our test t is equal to 2.98. So now we're going to use the critical value. So we need to determine if it's a left, right, or two-tailed. So it is a right-tailed because of the greater than. So we're trying to find this critical value. And our significance level is 0.01. So when we go into the calculator, we're going to go to second VARS, and we're going to go to INVT. Now, the area here is to the left, so it's 1 minus 0.01. Now, our degrees of freedom, we have n is 35 and n is 36. So the smaller n is 35, so 35 minus 1 is 34. And we end up getting that the critical value is 2.44. So this is 2.44. Where does our test statistic fall? Our test statistic falls over here in the reject region. So we are going to reject the null, which means we are looking at the claim here, which was our alternative. So we reject the null, and so we can say that there is sufficient evidence to support the claim that blue enhances performance on a creative task. And there's that sentence for you as well. Go ahead and give these two a try. You can use the p-value or the critical value method. I'll show my work for both. Press play when you're ready to see the solutions. And there you go. So that concludes section 9.2 part 1, and part 2 we'll be doing confidence interval estimates.